In this video, we are going to walk you through our project on action modeling using modular inverse reinforcement learning. This is our final project for reinforcement learning theory and practice. Let's get started. So, what are we doing in this project? Analysis of human actions in multitask settings such as gameplay to understand how humans prioritize different subtasks that lead to the end goal and how it relates to the actions. Why are we doing this? To achieve greater accuracy using the insights from human gameplay actions, which is typically hard to achieve by many black box algorithms. So how are we achieving this? We are using modular inverse reinforcement learning to infer the reward function and discount factor of different aspects of the freeway game and apply these rewards to achieve more accurate gameplay on the environment called arcade learning environment to test out the results. Moving ahead. So, to extract the state information from each individual game frame, we parse the image to get the x and y bounds of each objects as shown in the image on the right side. So basically, these bounds are nothing but the bounds of the highlighted rectangles of each object. Here, we are decomposing the game into two modules: the destination module and the reward and the car module. The destination module contains of the waypoints as its objects, which are shown in the figure, and the car module contains each car as its object. Now, a set containing the distances, the x and y distances from the agent to each object in both the modules is our representation of a state. So in a given state, we have the information about the distance between the agent and every object in both the modules. Coming to the action, the agent can take three possible actions. It can go up, it can go down, or it can stay right there.
So we're using modular RL as our method to achieve this. Modular RL takes on a Bayesian approach but adds modules to it. In this method, we want to find a set of solutions that maximizes the likelihood of seeing the behavioral data. In Bayesian RL, the likelihood function for a trajectory looks like this. In modular RL, we change the Q values for the whole state into the sum of Q values for all objects, which is more intuitive in the log likelihood function. In the original method, the discount factor is raised to the power of the Euclidean distance between the agent and the objects. However, this doesn't capture the dynamics of time and space in more complex domains because the discounts may not be uniform in spatial or temporal dimensions. So in our project, we are experimenting with separating the discount factor in the x and y dimension. So the Q value looks like this. For 10 trials of human demonstration data in the Atari HET dataset, we ran the modular RL algorithm for each of them. The average prediction accuracy was 77.1%. This is not a very high accuracy, especially with the imbalance breakdown for different actions. However, we later realized that prediction accuracy was not the best metrics to use. Despite the low accuracy, the average gameplay score was 26.4, which is statistically significantly higher than the other non-deep RL algorithms, which is shown in the slides. Besides using the modular RL algorithm, we also used a random search and came across a set of solutions that performed 32 points, and its behavior is highly human-like. Here's the video. In this video, we can see the agent playing the game, reaching the destination while avoiding the car, which is just like how humans would do it. So this results show that the modified version of modular RL algorithm works well for learning human behavior in multitask settings. In more complex domains, the discount factor may behave differently not only in spatial dimensions but also in time. For example, cars that move faster may have larger discount factors. We will test that hypothesis in the future. Second, because we changed the Q function, the log likelihood function is no longer convex, and we cannot rely on most of the regular optimizers to solve for the values. That's also why we tried the random search. If time permits, we should have used optimizers such as differential evolution. For next steps, we will be using the human gaze data to extract features instead of hand-coded features. We'll also try other games that have slightly more complex domains and see how the algorithm works out. Thank you for your time and have a good break.